Alright students, we're going to do a quick video. This is our second video on voting theory on fairness criteria. So you're going to have to copy some stuff down in your notebooks, but here we go. So we're going to learn about the 4 voting fairness criteria, which you're going to have to note down. And also we're going to define Arrow's impossibility theorem. And this is not to be confused with the green arrow. So here we go. So here are the 4 fairness criteria. So criteria is a plural, by the way, and then criterion is singular. It's Latin. Anyway, here are the 4 fairness criteria that must be met for a fair voting system. And we're going to talk about, there's a paradox here, why this can't work. So if a candidate receives a majority of first place votes, that candidate should be the winner. That seems fair. That's known as the majority criterion. So please write that down. Number 2, if a candidate is preferred in every one-to-one comparison with the other choices, that choice should be the winner. That's known as the Condorcet criterion. Number 3, if voters change their votes to increase the preference for a candidate, it should not harm that candidate's chance of winning. And that's known as the, it's hard to pronounce, monotonicity criterion. If a non-winning choice is removed from the ballot, it should not change the winner of the election. That is the independence of irrelevant alternatives, or the IIA criterion. These two seem to make sense. They all kind of make sense, but there's going to be a paradox here between these first two, and here's why. Ooh, purple. Okay, so Arrow's impossibility theorem. Again, not to be confused with the green arrow. So no voting system can satisfy all 4 fairness criteria in all cases. So there are certain situations where an election may seem unfair, but we have to live with it. So let's take a look. Here's an election where all of the votes cast, all of these voters got the same number of votes. They all got 10. So no candidate has a majority. In fact, they all got the same number of votes. Let's look at the one-to-one matchups. So A versus B. A received 30 votes to B. So if A was matched up against B, it would be 30 to 10. A versus C, 20 to 20. So if A is matched up against C, it would be 20 to 20. So what does that mean? So A versus C, 20 to 20, and A versus B, 30 to 10. How does that work? Well, let's take a look. See, A beats B in this election here. In these 10 ballots, A is above B. In these 10 ballots, A is below B. So A lost that one. A is above B in these 10 ballots, and A is above B in these 10 ballots. So A beats B, 30 to 10. A beats C 20 to 20, right? A is over C here, below C there, below C here, but above C in this one. So it's 20 to 20. And then A versus D, A actually loses out. So there's no Condorcet winner because on the one-to-one matchups, nobody wins all of them. And in fact, regardless of the candidate, 3/4 of the voters actually prefer somebody else, right? So if 10 voters prefer A, there's 30 that prefer the other candidate. So 3/4 actually prefer the other candidate. And this is called the Condorcet voting paradox. So again, I hope this helps explain some of these theorems and criteria. So please let me know if you have any questions. Thanks.